These are the answers to the AP Chemistry packet that covers topics 7.11 and 7.12. On this slide, you can see Unit 7 at a glance. Unit 7 is entitled Equilibrium. In this video, we will take a look at topic 7.11, Introduction to Solubility Equilibria, and topic 7.12, Common Ion Effect. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 7.11, Introduction to Solubility Equilibria. Here are some essential knowledge statements from the AP Chemistry course and exam description. The dissolution of a salt is a reversible process whose extent can be described by Ksp, the solubility product constant. The solubility of a substance can be calculated from the Ksp for the dissolution process. This relationship can also be used to predict the relative solubility of different substances. The solubility rules can be quantitatively related to Ksp, in which Ksp values that are greater than 1 correspond to soluble salts. See the essential knowledge statement from topic 4.7, Types of Chemical Reactions, shown below. Precipitation reactions frequently involve mixing ions in aqueous solution to produce an insoluble or sparingly soluble ionic compound. All sodium, potassium, ammonium, and nitrate salts are soluble in water. The molar solubility of one or more species in a saturated solution can be used to calculate the Ksp of a substance. On this slide, you can see a zoomed-in view of a beaker that contains calcium carbonate, both in insoluble solid on the bottom of the beaker and aqueous ions dissolved in the solution. So we are looking at this close-up particle view, there are particles of calcium carbonate in the solid form that are entering the solution to form aqueous ions. That process is known as dissolution, but there are also aqueous ions that are turning back into the solid form that's known as precipitation. So in a saturated aqueous solution of an ionic compound, a dynamic equilibrium is established between two opposing processes, dissolution, going from solid to aqueous ions, and precipitation, going from aqueous ions to solid. The equilibrium constant for the dissolution of an ionic solid is known as the solubility-product constant. It is written as Ksp, with the letters Sp representing solubility product. The equilibrium expression shows the product of the concentration of each ion, raised to the power of the coefficient from the chemical equation for the dissolution of the solid. Remember that solids are not included in the equilibrium constant expression. Question 1. Fill in the missing information in the table below. So we are given the name and the formula of 5 different ionic compounds, and we have to write the equation for the dissolution of the solid and also write the Ksp expression. Let's start with silver chloride. On the periodic table, we can find chloride in the halogen family in group 17, and we know that chloride has a charge of -1. Since the formula is AgCl in a 1-to-1 ratio, that means that the charge on the silver ion must be +1. So remember that the common charge that we see on the silver ion when it forms compounds is +1. So on the left of the equation, it's going to be the reactant, the solid AgCl. That's written as one formula, but then on the right side of the arrows, we see the separate ions with their charges. So we have Ag plus and Cl minus. Now, normally on the AP Chemistry exam, you're not required to put states of matter, such as solid, liquid, gas, aqueous, but in all of these examples, I am going to include the abbreviations for states of matter, because remember that solids are not included, as well as pure liquids, in the equilibrium constant expression. So by showing you AgCl solid, that's a reminder that that substance will not appear in the KSP expression. So we have concentration of silver times concentration of chloride. Don't forget to include charges on your ions. Our next example is lead Roman numeral 2 iodide. The Roman numeral 2 tells us that the charge on the lead ion is +2. On the periodic table, we can find in that same family, the halogen family group 17, iodide, and we know that iodide is -1. We know that lead is +2 both because of the Roman numeral and the fact that one lead has to counteract the charge on 2 iodide ions. So to keep the total charge equal to 0, the charge on the lead ion has to be +2 in this particular formula. So on the left, we have solid lead iodide, PbI2, and on the right, we have the lead ion with its charge and the iodide ion with its charge. Don't forget to include the charges on the ions. Don't forget to balance the equation. And again, I'm showing you the symbols for S for solid and AQ for aqueous to remind you that we include only the aqueous ions in the KSP and not the solid that is being dissolved. So it's going to be concentration of the lead ion times the concentration of the iodide ion squared, again, raised to the second power, because we always use the coefficients as exponents when we write either a Kc or a Kp. All right, our next example is another compound that contains silver. This is silver chromate. So remember that the charge on silver is +1. We have 2 of them in this formula. So if I have 2 silver ions that are each +1, that means the charge on the chromate ion, CrO4, must be -2 in order to balance the overall charge in that formula. So on the left of the arrows, I have solid silver chromate, Ag2CrO4, and on the right, I have 2 silver ions plus 1 chromate ion. Again, don't forget to balance the equation and always put the charge on your ions on the right side of this equation. The KSP would be concentration of silver squared, because of the coefficient of 2, times the concentration of chromate. The next one is chromium Roman numeral 3 hydroxide. That tells us that the charge on the chromium ion is +3. And each hydroxide is worth -1, so we have 3 hydroxide ions to balance out the overall charge. On the left, it'll be the formula for the chromium 3 hydroxide, solid, and on the right, it will be the chromium ion and 3 hydroxide ions. Again, don't forget to write the charges on your ions. Don't forget to balance the equation. So the KSP would be concentration of chromium times concentration of hydroxide raised to the third power. And our last example in this table is magnesium phosphate. We can find magnesium in group 2 on the periodic table, and magnesium's charge is +2. We have 3 of them in this formula. That's a total charge of +6. Therefore, each phosphate, we have 2 of them, is worth -3. In order to balance out the overall charge, we have 3 magnesium ions and 2 phosphate ions. So magnesium phosphate, Mg3PO4 parentheses 2 on the left, and 3 magnesium ions and 2 phosphate ions on the right. Again, don't forget to include the charge and balance the equation. The KSP will be concentration of magnesium raised to the third power times concentration of phosphate squared. All right, well, that is the answer to question 1. And so before I talk about question 2 in the packet, I just want to clarify an important difference between the solubility product constant, KSP, and the solubility of a compound. The KSP is the equilibrium constant for the dissolution of an ionic solid. The temperature at which KSP is reported is usually 25 degrees Celsius, and as you've learned already, there are no units for the equilibrium constant K. Now, the solubility refers to the concentration of a substance in a saturated aqueous solution at a certain temperature. Common units for the solubility of a compound are moles per liter, or molarity, capital M, or grams per liter. So again, the solubility product constant and solubility are not the same thing. Question 2. Answer the following questions related to the solubility of calcium hydroxide, CaOH in parentheses 2. Part A. Write a balanced chemical equation for the dissolution of solid calcium hydroxide in pure water. This is similar to the process that we used in question 1. So we're going to have the solid compound on the left and the aqueous ions with their charges on the right. So calcium is located in group 2, so it has a charge of +2. Hydroxide is -1, and we have 2 of them. So on the left will be the chemical formula, calcium hydroxide, solid, and on the right will be the individual ions, calcium and hydroxide. Don't forget to balance the equation, and don't forget to include the charges on your ions. We don't know the concentration of these ions yet, but we do know that, according to the stoichiometry, their concentrations are in a 1:2 mole ratio in solution when a pure sample of solid calcium hydroxide is dissolved in water. For every 1 mole of solid calcium hydroxide that dissolves, 1 mole of calcium ions are produced and 2 moles of hydroxide ions are produced. So the KSP for this compound would be concentration of calcium times concentration of hydroxide squared. Now we don't know what these numbers are, but for example, if the concentration of calcium were 0.10 molar, then the concentration of hydroxide would have to be twice as much, or 0.20 molar. If the concentration of calcium were 0.01 molar, the concentration of hydroxide would have to be twice as much, or 0.02 molar. The concentration of calcium were 1 times 10 to the negative 3 molar. The concentration of hydroxide would be 2 times 10 to the negative 3 molar. So since we don't know the concentrations, we can go ahead and set the concentration of calcium as X, and then the concentration of hydroxide would have to be 2X. At this point, if we do the math for X times the quantity 2X squared, we get 4X cubed, where X represents not only the concentration of calcium, but also the solubility in moles per liter of the entire compound. So this is our equation for the dissolution of calcium hydroxide. X would represent the solubility of calcium hydroxide in units of moles per liter. X would also represent the concentration of calcium ions in units of moles per liter. And the concentration of hydroxide ions in units of moles per liter would be 2X. And they were giving us in part B the value for the KSP for calcium hydroxide. It's 5.0 times 10 to the negative 6. Calculate the molar solubility of calcium hydroxide, which would mean we are basically solving for X in this problem to determine the molar solubility of calcium hydroxide. Now, this is a zoomed in particle view of the aqueous portion of this saturated solution. And so we see aqueous ions of calcium. There happen to be 4 in this particle diagram. And we see aqueous ions of hydroxide, and there happen to be 8. So there will always be a 1:2 ratio of calcium hydroxide. If you dissolve pure calcium hydroxide solid in water, you will always get that 1:2 ratio. So the calcium would be X and the hydroxide would be 2X. The next step in the process for solving for X, after we've set 4X cubed equal to the number 5.0 times 10 to the negative 6, is to divide both sides of the equation by 4. And when we do that, we get X cubed is equal to 1.25 times 10 to the negative 6. Now we'll take the cube root of that number to solve for X. So X is equal to the cube root of 1.25 times 10 to the negative 6. And this is the concentration or the solubility of this entire compound. 0.010772 moles per liter. I'm going to round that off to two significant figures. So I'll say 0.011 moles per liter. So that number represents not only the solubility of calcium hydroxide in units of moles per liter, that number is also the concentration of calcium ions in solution. The concentration of hydroxide ions in solution would be twice as much, or 0.022 moles per liter. Now that we know the molar solubility in moles per liter, we're going to calculate the solubility in units of grams per liter. So the answer to part B is 0.011 moles of calcium hydroxide for every 1 liter of solution. We're looking for a conversion factor that will change it from moles per liter to units of grams per liter. What we need to do is get rid of the mole and convert that to grams, but we're not going to change liters at all. So we have to get rid of mole, so put mole on the bottom and grams on top. This means that we have to consult the periodic table to calculate the molar mass of calcium hydroxide. And when we do that math, we add up the atomic mass of calcium and 2 times the atomic mass of oxygen and 2 times the atomic mass of hydrogen. We get 74.096 grams per mole. Now, if we take 0.011, which was the answer to part B, and we multiply by the molar mass, 74.096 grams per mole, we get 0.81506 grams of calcium hydroxide per liter. And when I round that off to two significant figures, I get 0.82 grams per liter. Now, if I had taken a little bit more precision with my answer to part B, in other words, if I had taken on my calculator a longer, less rounded version of that number for the solubility of calcium hydroxide, for example, 0.01077 moles per liter, if I multiply this value by the molar mass of calcium hydroxide, I get a slightly different answer. Because of the way I rounded, I now get 0.80 grams per liter. So either of those answers are acceptable. I just wanted to remind you that sometimes when you round off a final answer, you're done. But if you use that number in a subsequent calculation, then it might be a little bit different if you use the rounded version, which had 2 significant figures, or the unrounded answer that had more significant figures. So there's my answer to part B and part C. So part B is 0.011 moles per liter for the solubility of calcium hydroxide and approximately 0.8 grams per liter for the solubility in different units of grams per liter. Now, some of the questions that you will see in this packet are more about calculations and conversions. For example, can you take the KSP and calculate the molar solubility? Or can you convert from units of moles per liter to grams per liter? But then there are other questions in this packet that are much more conceptual. Do you understand the idea of a saturated solution? So parts D and E of question 2 are much more conceptual. Let's take a look. It says a beaker contains 100 milliliters of a saturated solution of calcium hydroxide at 25 degrees Celsius with a small amount of undissolved solid calcium hydroxide present at the bottom of the beaker. The beaker is warmed gently and some of the water evaporates so that the volume of the solution decreases to 75 milliliters. The beaker is allowed to sit at room temperature until the temperature returns to 25 degrees Celsius. So part D says, is the value of the concentration of the calcium ions in the 75 milliliter sample of solution on the right in the diagram above less than, greater than, or equal to the value of the concentration of calcium ions in the 100 milliliter sample of solution on the left in the diagram above? Justify your answer. So what I'm going to show you now is from Unit 3, where I taught you about solutions and concentrations. And when you're doing a dilution, you would use what I would call the dilution equation. So the molarity of the concentrated solution times the volume of the concentrated solution is equal to the molarity of the dilute solution times the volume of the dilute solution. So because of that inverse relationship between molarity and solution volume, you might be tempted in this part of this question to assume that since the volume of the solution decreased from 100 milliliters to 75 milliliters, that this would cause the concentration of the calcium hydroxide to increase. Well, if you say increase or greater than for that solution that is on the right, the 75 milliliter sample, then you're assuming that the solution is more concentrated on the right than on the left. But you're not understanding the concept of saturation. So let me go ahead and define this for you. A solution that is in equilibrium with undissolved solid solute is saturated. A saturated solution contains the maximum amount of solute that can dissolve in a given amount of the solvent at a certain temperature. So the solution on the left with a volume of 100 milliliters is saturated. And again, you can see a little bit of undissolved solid at the bottom of the beaker. But the solution on the right is still saturated. So it's not possible to increase the concentration of the solution. If it's already saturated before, it's still saturated afterwards. So the correct answer to part D is the following. The value for the concentration of calcium ions in the 75 milliliter sample of solution is equal to the value of the concentration of calcium ions in the 100 milliliter sample of solution. Each solution is saturated. The concentration of the solute particles in a saturated solution depends on the value of KSP and not the volume of the solution. So it doesn't matter whether we have 100 milliliters or 1,000 milliliters. If it's saturated, then the concentration of the calcium ions in those solutions would be the same. It's determined by the value of KSP and not the volume of that saturated solution. Now that I have explained the answer to part D, I think it'll make part E much easier to understand. Here is the situation for part E. It says a beaker contains 75 milliliters of a saturated solution of calcium hydroxide at 25 degrees Celsius with a small amount of undissolved solid calcium hydroxide at the bottom. Water is added to the beaker, and the mixture is stirred thoroughly. The volume of the solution increases to 100 milliliters. A small amount of undissolved solid calcium hydroxide is present at the bottom of the beaker. So part E says, is the value for the concentration of calcium 2+ ions in the 100 milliliter sample, which is on the right, less than, greater than, or equal to the value for the concentration of calcium ions in the 75 milliliter sample of solution, which is on the left. Justify your answer. So water was added, and you might be tempted to assume that this will decrease the concentration of the calcium ions in solution because we've added water. But look at the bottom of the beaker on the right. There is still a sample of undissolved solid calcium hydroxide at the bottom of that beaker, so it remains saturated. So some, but not all, of the solid calcium hydroxide that was on the bottom of the beaker probably did dissolve when additional water was added, but it didn't all dissolve completely. So there is still some solid calcium hydroxide present. Therefore, the beaker on the right, even though it has a larger volume of solution, it still remains saturated. So the answer to part E is very similar to the answer to part D. Take a look. The value for the concentration of calcium ions in the 100 milliliter sample of solution is equal to the value for the concentration of calcium ions in the 75 milliliter sample. Each solution is saturated, and again, the concentration of solute particles in a saturated solution depends on the value of KSP and not on the volume of the solution. Now, in question 2 of this packet, we were given the value of KSP for a compound, and we had to calculate the solubility of that compound. Here, in question 3, it'll be the reverse process. In question 3, you will be given the solubility of a compound, and then eventually you will have to calculate the KSP for that compound. All right, this is question 3. Answer the following questions related to the solubility of silver carbonate, Ag2CO3. Part A, write a balanced chemical equation for the dissolution of silver carbonate in pure water. So it's going to be the solid compound on the left of the arrow. Remember that the charge on the silver ion is +1, and that makes the charge on the carbonate ion -2, because there are two silvers that are each worth +1, so the charge on carbonate has to balance the charge on two silver ions. So on the left of the equation, we have the solid silver carbonate compound, and on the right, we have the aqueous ions. Don't forget to balance the equation, and don't forget to include the charges. So 1 mole of silver carbonate produces 2 moles of aqueous silver ions and 1 mole of aqueous carbonate ions. So in part B, we are given the solubility in units of grams per liter. First, we're going to convert that into units of moles per liter, and then in part C, we're going to calculate the value of KSP for this compound. So we're going to start with grams per liter and then calculate the molar solubility in units of moles per liter. 0.035 grams of silver carbonate for every 1 liter. And then our final answer should have units of moles of silver carbonate per liter. This time we want grams on the bottom and moles on top in our conversion factor. We're going to consult the periodic table and figure out the atomic mass of silver times 2 plus the atomic mass of carbon plus 3 times the atomic mass of oxygen. And so when we do that, we'll put our molar mass on the bottom and 1 mole on top. So the molar mass of silver carbonate works out to be 275.75 grams. So we're going to cross off the units of grams and go to moles. When you pick up your calculator and you'll do 0.035 divided by the molar mass of 275.75, you get 1.269 times 10 to the -4 moles of silver carbonate per liter. Let's round that off to 2 significant figures. So 1.3 times 10 to the -4 moles per liter. That is the molar solubility of silver carbonate. Now with respect to the X and the 2X, let's talk about that. So X would represent the solubility of the entire compound in units of moles per liter. 2X would represent the concentration of aqueous silver ions in solution in units of moles per liter, and X would represent the concentration of aqueous carbonate ions in units of moles per liter. So we already have the solubility of silver carbonate in units of moles per liter. That was 1.3 times 10 to the -4 moles per liter. According to the stoichiometry of the dissolution equation, the concentrations of the silver ion and the carbonate ion are in a 2-to-1 mole ratio. So when 1 mole of silver carbonate is dissolved in water, 2 moles of aqueous silver ions are produced, and 1 mole of aqueous carbonate ions are produced. So we're going to take that 1.3 times 10 to the -4 moles per liter, and that would be represented by the concentration of the carbonate on the right because of that 1-to-1 ratio between silver carbonate and carbonate itself, but then it's double that value for the concentration of silver in solution. That would be 2.6 times 10 to the -4. And now that we know that the concentration of silver is 2.6 times 10 to the -4 moles per liter, and the concentration of carbonate is 1.3 times 10 to the -4 moles per liter, we can plug in those values into the KSP expression and calculate the value of KSP for silver carbonate at 25 degrees Celsius. So the KSP equals the concentration of silver squared times the concentration of carbonate. That's going to be 2.6 times 10 to the -4 squared times 1.3 times 10 to the -4. And when you do that math to calculate the KSP, you get approximately 8.788 times 10 to the -12. I will round that off to 2 significant figures. So I'll say 8.8 times 10 to the negative 12. And if you had used a little more precision or less rounded answers to calculate the KSP, so for example, 2.538 times 10 to the negative 4 squared, and then 1.269 times 10 to the negative 4, you would have gotten a slightly different answer for KSP. So I'm showing you that either 8.8 times 10 to the negative 12 or 8.2 times 10 to the negative 12. Both of those answers would be acceptable. It just depends on whether or not you used a rounded answer with two significant figures or a less rounded answer with more precision and more significant figures. But both of those numbers would be acceptable because they do represent that you understand the concept and that 2-to-1 ratio of silver to carbonate, as well as the fact that you have to square the concentration of silver and then multiply by the concentration of carbonate. All right, this is question 4. And question 4 says the following. Saturated solutions of each compound listed in the table above were prepared at 25 degrees Celsius. Use the information in the table above to answer the following questions. Part A, which compound, so it's calcium fluoride, CaF2, strontium fluoride, SrF2, or barium fluoride, BaF2, which compound has the smallest value for molar solubility in water at 25 degrees Celsius? Justify your answer. So in this particular question, it is fortunate that each of these three compounds that we are comparing has the same mole ratio for its positive ions, cations, and negative ions, anions. There is a 1-to-2 ratio. So whether it's calcium fluoride, strontium fluoride, or barium fluoride, there is that 1-to-2 ratio between the positive ion and the negative ion. So in general, we're going to get the solubility of the metal fluoride, X. The concentration of the metal aqueous ion will be X. And the concentration of the fluoride ion in solution will be 2X. That makes X times the quantity 2X squared for the KSP equal to 4X cubed. No matter which solid compound we choose, X would represent the solubility of the compound. So we are able to compare the different values of KSP in the table. And because each compound has the same mole ratio for its cations and anions, we can choose the compound that has the smallest value for molar solubility will be the one that has the smallest value for KSP. So 3.9 times 10 to the negative 11 is the smallest value. So that makes calcium fluoride the correct answer to part A. So what I'm saying here is that each compound has the same 1-to-2 molar ratio for its cations and anions. Calcium fluoride should have the smallest value for molar solubility because it has the smallest KSP value. Now in question 5, when we get to question 5, you will notice that it's going to be a little bit different if you're comparing two different compounds that have different mole ratio for its cations and anions. But right now in question 4, they all had the same 1-to-2 molar ratio for cations and anions, so we could compare the KSP values and say the smallest value for molar solubility is going to be the one that has the smallest KSP. Now let's go on to part B of this question. Calculate the concentration of the fluoride ion in moles per liter in a saturated solution of the compound that you selected in part A. So here is our KSP expression. For calcium fluoride, it's concentration of calcium ions times concentration of fluoride ion squared. That would be X times the quantity 2X squared, or 4X cubed. We set that equal to the KSP, which is 3.9 times 10 to the negative 11, and now we proceed to solve for X. I will divide both sides of the equation by 4. So I get 3.9 times 10 to the negative 11 divided by 4 is 9.75 times 10 to the negative 12, and that equals X cubed. So if X cubed equals 9.75 times 10 to the negative 12, let's take the cube root of that number. So the cube root of 9.75 times 10 to the negative 12 is equal to 2.136 times 10 to the negative 4 moles per liter. Now, just because we solve for x on our calculator does not necessarily mean that we have arrived at our final answer. And so remember that the equation for the dissolution of solid calcium fluoride produces 1 mole of calcium ions, but 2 moles of fluoride ions. So X would represent the solubility of calcium fluoride in moles per liter. X would also represent the concentration of calcium ions in moles per liter, but the concentration of fluoride ions in this solution would be equal to 2x. So we have solved for x, which is approximately 2.1 times 10 to the negative 4 moles per liter, but since we're trying to find the value for the concentration of fluoride, it would be, let's take that number for x and multiply by 2. So the correct answer to part B is going to be approximately 4 times 10 to the negative 4. And depending on how you rounded your final answer, you might have gotten possibly 4.28 times 10 to the negative 4, or maybe just 4.2 times 10 to the negative 4 moles per liter. So that is the answer to part B, the concentration of fluoride. In question 4, all 3 compounds that were being compared had the same 1:2 molar ratio between cations and anions. In question 5, that's not going to be the case. Let's take a look at question 5. Question 5 says the following. Saturated solutions of each compound listed in the table above were prepared at 25 degrees Celsius. Use the information in the table above to answer the following questions. Part A. Without doing any calculations, predict which solution contains a higher concentration of the chromate ion, CrO4 2-. So just focusing on the KSP, it's 1.1 times 10 to the negative 12 for silver chromate, and it's 1.2 times 10 to the negative 10 for barium chromate. So if I think that the larger the KSP, the greater the solubility of the compound, then I would pick barium chromate. I'm not saying that barium chromate is the correct answer, but that's what I would predict without picking up my calculator and just comparing the magnitude of the KSP values. Now, we should pick up our calculator and see what's going on here because these have different mole ratios for cations and anions. So back in question 4, each compound had the same ratio of cations to anions in their formulas. It was all 1:2. But silver chromate, the ratio of silver to chromate is 2:1. Barium chromate, the ratio of barium to chromate is 1:1. So the math is going to be different, which means we actually cannot assume anything until we pick up our calculator and do the math. So for silver chromate, X represents the solubility of the entire silver chromate compound. 2x represents the concentration of silver ions in that saturated solution, and X represents the concentration of chromate ions in that saturated solution. Now for barium chromate, X represents all 3, the solubility of the entire compound, the concentration of barium, and the concentration of chromate because of the 1:1 mole ratio. Now let's go ahead and do the math, starting with silver chromate. We're going to take the KSP for silver chromate, and we're going to set that equal to 4x cubed and solve for x. And when we do barium chromate, it's going to be the KSP for barium chromate equal to x squared. So we should get different math manipulations. In one case, we're dividing by 4 and taking the cube root. In the other case, we're just taking the square root. All right, let's start with silver chromate. The KSP is 1.1 times 10 to the negative 12. We set that equal to 4x cubed, divide by 4, and then take the cube root. So when I do that math on my calculator, 1.1 times 10 to the negative 12 divided by 4 is 2.75 times 10 to the negative 13th. I take the cube root, and I get approximately 6.5 times 10 to the negative 5 moles per liter. Now for the barium chromate, all I have to do is take the square root of the KSP. And when I do that math, the square root of 1.2 times 10 to the negative 10 is approximately 1.1 times 10 to the negative 5. So now that we have done the math on our calculator for these two different compounds in which there are different mole ratios for the cations and the anions, we discover, perhaps a little bit to our surprise, that it was the silver chromate that actually had the smaller value of KSP that contained the larger concentration of chromate. So the message here, looking at these two calculations side by side, is that when you are comparing different KSP values for different compounds, make sure that the compounds have the same mole ratio of cations to anions. And if they do, then you can just look at the KSP values to determine which one has the highest or the lowest solubility for that compound. But as we saw in question 5, if the compounds that you're comparing have different mole ratios for the cations and the anions, go ahead and pick up your calculator, do the calculation, make sure your values are correct so that you would discover the actual concentration of a particular ion and not just simply look at the KSP values. Question 6. Answer the following questions about the reaction between aqueous sodium sulfate, Na2SO4, and aqueous barium nitrate, Ba parentheses NO3 2. Part A. A student adds an excess amount of aqueous sodium sulfate to a solution of aqueous barium nitrate, resulting in the formation of a precipitate. Write the net ionic equation for the reaction that occurred in this experiment. So what I'm going to start with are the chemical formulas that we are given, which is sodium sulfate, Na2SO4, and barium nitrate, BaNO3 inside parentheses times 2. And so we have sodium, which is +1, as you know on the periodic table. Sodium's in group 1. We have 2 sodiums and 1 sulfate. The charge on the sulfate ion is -2. Then we have 1 barium, which is +2. It's located in group 2. And we have 2 nitrate ions, and each nitrate is worth -1. So those are the formulas. And I'm putting them outside the box because I'm not quite ready to write the net ionic equation just yet. Now, for this reaction, sodium has a new partner on the other side of the equation, which is nitrate. That would be NaNO3. And then barium has a new partner on the other side of the equation, which is barium sulfate, BaSO4. Notice that the charge balances +1 and -1, +2 and -2, but I still need to balance the overall equation, so I need 2 moles of sodium nitrate on the right to balance the overall equation. So here is my balanced equation, but I'm going to put question marks inside the symbols for either AQ or S. We know there's a precipitate, and we know that one of the compounds is insoluble and the other compound is soluble. You may remember from Unit 4, talking about net ionic equations, that you have the so-called snap ions, so sodium, nitrate, ammonium, and potassium. Those 4 ions are soluble. So if sodium and nitrate is one of the snap ions, those are soluble, then sodium nitrate gets the AQ, and barium sulfate must be the precipitate. So I put S for solid. So now I'm going to write the net ionic equation for the production of solid barium sulfate. On the right side of the equation, I have barium sulfate solid. On the left side of the equation, I have the aqueous ions that were combined to form barium sulfate. So the spectator ions of sodium and nitrate would have been crossed off on both sides of the complete ionic equation, so the spectator ions do not appear in the net ionic equation because they remain soluble the entire time. So you may have noticed that while this is the formation of barium sulfate, it's actually the reverse of the equation for the dissolution of an ionic solid. So barium sulfate, when dissolved in water, would produce the aqueous ions. And the KSP for barium sulfate would be concentration of barium times concentration of sulfate. So in question 6, one of the things that we will have to do is to compare the value of Q with the value of K. Specifically, QSP and KSP will be compared. So in part A, it said a student adds an excess amount of sodium sulfate to a solution of barium nitrate, and there was a precipitate. But that's because an excess amount of sodium sulfate was added. If you combine a certain amount of sodium sulfate and barium nitrate, it may or may not produce a precipitate depending on this comparison between Q, SP, and KSP. So to remind you about the Q versus K comparison, there are 3 possibilities. When you compare Q versus K, either Q is equal to K and the system has already reached equilibrium. For the KSP, that would mean that you are exactly at the saturation point. But more likely, you'll have one of the following possibilities, which is if Q is less than KSP, then the equilibrium would favor the formation of products from left to right, from reactants to products. And since on the right side of the equation are soluble aqueous ions, if Q is less than KSP, it means that no precipitate will be formed. And then if the reverse is true, if Q is greater than KSP, then now the net conversion of products to reactants would result in the formation of a solid, so a precipitate would be formed. And we'll see this coming up, that Q versus K allows us to compare whether or not a precipitate will form. So we'll see that in the later parts of question 6. All right, so this is parts B and C. In a separate experiment, a 200.0 milliliter sample of 3.0 times 10 to the negative 6 molar barium nitrate, that's in the beaker on the left, is added to 150.0 milliliters sample of 2.0 times 10 to the negative 5 molar sodium sulfate. That's the beaker in the middle. So those 2 solutions are combined. The mixture is stirred to ensure that it's thoroughly mixed. Now, is a precipitate going to form? We don't know yet. We're going to be doing some calculations to get closer to that Q versus K comparison, but we don't know for sure if a precipitate will be formed. So parts B and C are to calculate the number of moles. Part B, number of moles of barium ions in that first beaker on the left, and then part C, number of moles of sulfate ions in that beaker in the middle. So before we do these mole calculations in parts B and C, just another reminder about what's going on. Here's a particle level view of the solutions in each beaker. So in the beaker on the left, that's barium nitrate. So we can see in the particle level view that there are barium ions and nitrate ions in a 1:2 ratio. Water molecules are not shown in the particle diagram. In the other beaker of sodium sulfate, there are sodium ions and sulfate ions in a 2:1 ratio. But it's the barium ions from one beaker that could combine with the sulfate ions in the other beaker that may produce a precipitate. We're not sure yet. Notice that even though the formula of barium sulfate is BaSO4, the number of moles of barium will not necessarily be equal to the number of moles of sulfate. And that's because they're coming from 2 different solutions with different concentrations. So the fact that barium is in one beaker and sulfate is in another beaker, that means that the number of moles of those ions do not have to be the same. They're not going to be necessarily in a 1:1 ratio because they're coming from 2 different sources, and different solutions have different concentrations. So it is possible that a precipitate of barium sulfate could be formed when these 2 solutions are combined, but we won't know for sure until we calculate the value of QSP and then compare the value of QSP with the value of KSP. All right, so back to parts B and C of this question. Volume, 200.0 milliliters. I'm first going to convert from volume of milliliters into liters. So I'm going to multiply by 1 liter over 1,000 milliliters. Then I will use the molarity as a conversion factor to go from volume to moles. So 3.0 times 10 to the negative 6 moles of barium nitrate for every 1 liter. Now, if I stop right now and did the calculation of 200 divided by 1,000 times 3.0 times 10 to the negative 6, I would have an answer in units of moles of barium nitrate. Now, they just want the number of moles of barium ions, but I would get the same value if I didn't do this last step because it's just a 1-to-1 ratio. I'm just showing you that in that formula for barium nitrate, there is 1 mole of barium ions present for every 1 mole of barium nitrate. So 200 divided by 1,000 times 3.0 times 10 to the negative 6, that gives me 6.0 times 10 to the negative 7 moles of barium. All right, now we'll do a very similar but parallel calculation in part C. The volume is 150.0 milliliters. First, I will convert from milliliters to liters by dividing by 1,000. Then I will use the molarity as a conversion factor to go from liters to moles. So 2.0 times 10 to the negative 5 moles of sodium sulfate for every 1 liter. Now we're trying to focus on sulfate and not sodium. So there is no subscript outside sulfate or parentheses. So there's 1 mole of sulfate for every 1 mole of sodium sulfate. So 150 divided by 1,000 times 2.0 times 10 to the negative 5 moles per liter. And I cross off my liters and my milliliters and I get moles. 3.0 times 10 to the negative 6 moles of sulfate. Now, these answers to part B and part C, they are not molarity. They are not concentration. They are just moles. Remember that concentration is normally in units of moles per liter. So right now in part B and part C, we don't have molarity, we just have moles. So here comes the next part, part D. The volume of the mixture formed in this experiment would be 200 plus 150. For a total volume of 350 milliliters. If we go back to our answers to parts B and C, we can divide the number of moles of each ion by the total volume in liters. So 350 milliliters becomes 0.3500 liters, and the number of moles from part B was 6.0 times 10 to the negative 7 moles of barium. When I divide by 0.35, I get 1.7 times 10 to the negative 6 moles per liter. So that is the concentration of barium in the mixture at the moment that the two solutions are combined, but before any chemical reaction occurs. So from part C, it was 3.0 times 10 to the negative 6 moles of sulfate divided by the total volume, 0.3500 liters, and I get the concentration of sulfate 8.6 times 10 to the negative 6 moles per liter. So now I have concentration of barium, concentration of sulfate at the moment that the two solutions are combined, but before any chemical reaction occurs. So now I can use these values that I just got in part D to plug it into the KSP expression, but I'm going to call it QSP for this moment in time. So here comes part E. Remember that we're going to compare Q versus K to determine whether or not a precipitate is formed. So if Q is less than KSP, then dissolution of the solid is favored and no precipitate would form. If Q is greater than KSP, then precipitation of the solid is favored and I would see a precipitate. So the answers to part D were the following numbers: 1.7 times 10 to the negative 6 for the concentration of barium, and 8.6 times 10 to the negative 6 moles per liter for the concentration of sulfate. We multiply them together, concentration of barium times concentration of sulfate. I'm calling this Q, so QSP for this moment in time, and I get 1.5 times 10 to the negative 11. So that is my value for the reaction quotient QSP. Let's compare that to the value of KSP. So in part F, we just calculated in part E the value of the reaction quotient QSP. Part F says the value of KSP for barium sulfate is 1.1 times 10 to the negative 10. Will a precipitate of barium sulfate be formed in this experiment? Justify your answer by comparing QSP with KSP. So since 1.5 times 10 to the negative 11 is less than the value of KSP, which is 1.1 times 10 to the negative 10, if Q is less than KSP, then no precipitate will be formed. So since the value of QSP is less than the value of KSP, a precipitate of barium sulfate will not be formed. So first, for the guidelines for determining if a precipitate will form when two solutions are combined together, determine the identity of the ions that can react together to form a precipitate. So it will not be a compound that contains any of those soluble snap ions. So not sodium or nitrate or ammonium or potassium. Once you've identified the ions, then those ions should be present in the KSP expression. Calculate the initial concentration in moles per liter for each ion in the combined solution before any reaction occurs. And if Q is greater than KSP, then yes, a precipitate will form. And if Q is less than KSP, then no, a precipitate will not form. All right, now let's take a look at our next question in this packet. This is question 7. Question 7 in this packet was taken from free response question 7, which appeared on the 2023 AP Chemistry exam. There is an address on this slide, and free response questions and scoring information from past AP Chemistry exams can be found by visiting the following website. In question 7, it says strontium hydroxide dissolves in water according to the following equation. The KSP expression for strontium hydroxide is provided. In part A, it says a student draws the particulate diagram shown at right to represent the ions present in an aqueous solution of strontium hydroxide. Water molecules are intentionally omitted. Identify the error in the student's drawing. So we can see, based on the chemical formula of strontium hydroxide, that there should be a 1:2 mole ratio between the strontium ions and the hydroxide ions. But in the student's drawing, they show 4 strontium ions and 4 hydroxide ions, which is a 1:1 ratio as opposed to a 1:2 ratio. What you can see on this slide are the official scoring guidelines from the 2023 AP Chemistry free response question number 7. So the answer to part A is the following. The error in the student's drawing is that the student's drawing shows an incorrect ratio of strontium and hydroxide ions, or you could also say that the student's drawing is not charged balanced. In other words, if you have 4 strontium ions and each strontium has a charge of +2, 4 times +2 is +8. But if you have 4 hydroxide ions and each hydroxide ion has a charge of -1, 4 times -1 is -4. So with a +8 and a -4, the student's drawing is not charged balanced. Okay, well, this is the answer to part A. Now let's take a look at part B of this question. In part B, it says the student prepares a saturated solution of strontium hydroxide by adding excess solid strontium hydroxide to distilled water at 25 degrees Celsius and stirring until no more solid dissolves. The student then determines that the concentration of the strontium ion is equal to 0.043 moles per liter in this saturated solution. So in part I of part B, it says calculate the value of the concentration of the hydroxide ion in this saturated solution. And then part II says to calculate the value of KSP for strontium hydroxide at 25 degrees Celsius. So to calculate the concentration of the hydroxide ion in the solution, all we have to do is recognize that there is a 1 to 2 mole ratio between strontium ions and hydroxide ions in the solution. So we can create a conversion factor that says there are 2 moles of hydroxide ions in the solution for every 1 mole of strontium ions in the solution. So all we're doing is multiplying by 2. 0.043 times 2 is equal to 0.086. So the concentration of the hydroxide ion in this saturated solution is twice as much as the concentration of the strontium ion. So 0.086 moles per liter is the answer to part B-I. So here is the official scoring guidelines from question 7 from the 2023 AP Chemistry exam, and you can see that that's exactly how they solved part B-I, to multiply the concentration of the strontium ion in the saturated solution by 2 based on that 2 to 1 mole ratio between hydroxide and strontium in this saturated solution. Now, on to part B-I, which says to calculate the value of KSP for strontium hydroxide at 25 degrees Celsius. We are given the KSP expression in this problem, although that wasn't necessary. You should know how to write the KSP expression for strontium hydroxide based on the fact that it's going to be the concentration of strontium times the concentration of hydroxide squared. And then we can plug in the values that we know for the concentration of each of these ions and calculate KSP. So the concentration of strontium is 0.043. The concentration of hydroxide is 0.086. So this is the math that we're going to do in our calculator. 0.043 times 0.086 squared. And when we do that math, we get 0.000318, or you could write this in scientific notation as 3.18 times 10 to the negative 4. Remember that the equilibrium constant is a dimensionless quantity, so it does not have any units. Let's go ahead and take a look at the official scoring guidelines for this question, and you can see that that's exactly what they did to calculate the answer. They rounded off their final answer for KSP to 2 significant figures. So again, the answer to part B-I is 0.00032, or in scientific notation, 3.2 times 10 to the negative 4. All right, now let's take a look at part C of this question. It says the student prepares a second saturated solution of strontium hydroxide in aqueous 0.10 molar strontium nitrate instead of distilled water. Will the value of the concentration of the hydroxide ion in the second solution be greater than, less than, or equal to the value in the first solution? Justify your answer. Assume that the temperature remains constant at 25 degrees Celsius. So let me give you a visual that can help you understand what's the difference between the first saturated solution of strontium hydroxide and the second saturated solution of strontium hydroxide. So here you can see 2 beakers in which a solid sample of strontium hydroxide is being added to each beaker. So in the first saturated solution, excess solid strontium hydroxide is added to distilled water to prepare a saturated solution. But then in the second experiment, excess solid strontium hydroxide is added to 0.10 molar strontium nitrate to prepare a saturated solution. So you should be thinking about how the equilibrium system for the dissolution of strontium hydroxide is affected if there are extra strontium ions already in the solution when that saturated solution of strontium hydroxide is prepared. Now, this might remind you of Le Chatelier's principle. So in an earlier video where I was talking about topics 7.9 and 7.10, there were quite a wide variety of examples of a stress imposed on an equilibrium system and then how the equilibrium system responds to the stress. So consider this row of the table. If additional product is added to an equilibrium system, then Q becomes greater than K, and the system would experience a shift from right to left. In other words, there should be a net conversion from products to reactants, and that's what's going on in this particular situation. So as you can see, on the left, we have solid strontium hydroxide in this equation, and on the right, we have both aqueous strontium ions and aqueous hydroxide ions. So in that solution, there are already present strontium ions from 0.10 molar strontium nitrate. So if there are strontium ions already present in solution, then this will cause a shift in the equilibrium for the dissolution of strontium hydroxide. And it will cause a shift from products to reactants or from right to left. So therefore, strontium hydroxide will be less soluble in a solution that already contains strontium ions in it than it would be in pure water. Now, what I really like about this particular question, so number 7, part C, is it's a great transition to the next topic that we will be discussing in this video, topic 7.12, the common ion effect. So it says the solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present in the salt. That's exactly what's happening in number 7, part C. So the impact of this, quote, common ion effect on solubility can be understood qualitatively using Le Chatelier's principle or calculated from the KSP for the dissolution process. So here is the answer to number 7, part C. Will the value of the concentration of the hydroxide ion in the second solution be greater than, less than, or equal to the value from the first solution? Strontium hydroxide will be less soluble in a solution that already contains strontium ions in it as compared to the solubility of strontium hydroxide in distilled water. And this is an example of the common ion effect. So therefore, the value of the concentration of the hydroxide ion in the second solution will be less than the value of the concentration of hydroxide in the first solution. Here, on this slide, you can see the official scoring guidelines for question 7 from the 2023 AP Chemistry exam. And so for part C, it says less than, again, that was the answer, because the strontium nitrate solution already contains a common ion. In other words, there are already strontium ions present in the solution. The solubility of the strontium hydroxide will be decreased, resulting in a lower value for the concentration of the hydroxide ion. All right, well, that's the answer to number 7, part C. So now, let's go ahead and officially make the transition to our next topic in this packet. This is topic 7.12, common ion effect. So as I said earlier, the solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present in the salt. The impact of this common ion effect on solubility can be understood qualitatively using Le Chatelier's principle or calculated from the KSP for the dissolution process. Now let's take a look at question 8 in your packet. It says the value of KSP for lead bromide, which has the chemical formula PbBr2, is 1.9 times 10 to the negative 5 at 25 degrees Celsius. A saturated solution is prepared by adding excess solid lead bromide to distilled water at 25 degrees Celsius and stirring until no more solid dissolves. In part A, it says fill in the values in the table below. So we need to calculate the concentration of the lead ion and the concentration of the bromide ion in a saturated solution of lead bromide at 25 degrees Celsius. Let's begin by writing the chemical equation for the dissolution of solid lead bromide in water. So we have solid lead bromide, PbBr2, on the left, and then we have the aqueous ions, lead and bromide, on the right. Remember that since we don't know the concentration of these ions, but we do know that they are in a 1:2 ratio in terms of the relative number of moles, then we can consider the concentration of lead to be X and the concentration of the bromide ion to be 2X. Now let's write the KSP expression, and we know that that is equal to the concentration of the lead ion times the concentration of the bromide ion squared. And that's equal to 1.9 times 10 to the negative 5 because they gave us the value of KSP in this question. So let's go ahead and substitute X and 2X for the concentration of the lead and the concentration of the bromide. So we have X times the quantity 2X squared. So mathematically that is equal to 4X cubed. And that is equal to 1.9 times 10 to the negative 5. All we have to do now is solve for X. So let's divide by 4 and then take the cube root of that value. So 1.9 times 10 to the negative 5 divided by 4 is equal to 4.75 times 10 to the negative 6. And if we take the cube root of that number, we get 0.0168, and that represents X, which is the concentration of the lead ion in this saturated solution. So 0.0168 moles per liter. Based on that 1:2 ratio, the concentration of the bromide ion in this saturated solution should be twice as much. So 0.0168 times 2 is equal to 0.0336 moles per liter. So these are the answers to part A. If we decide to round off our final answer to 2 significant figures, then we would get 0.017 and 0.034 for the concentration of lead and the concentration of bromide, respectively. Now let's take a look at part B of this question. In part B, it says a small amount of solid sodium bromide is added to 100 milliliters of the saturated solution of lead bromide, and the mixture is stirred thoroughly. Assume a constant temperature of 25 degrees Celsius and that the change in volume is negligible. Should the value of the concentration of the lead ion decrease, increase, or remain the same after the small amount of solid sodium bromide is added? Justify your answer. So here is a diagram to help you understand what's going on. We have a saturated solution of lead bromide that has been prepared, and then a small amount of solid sodium bromide is added to the solution. Now, we can assume that since sodium is one of those soluble snap ions, that the sodium bromide will dissolve when the mixture is stirred thoroughly. And so therefore, we have in our equilibrium system a stress that has been imposed. So think about how this equilibrium system for the dissolution of lead bromide is affected if additional bromide ions are added to the solution in the form of this small amount of sodium bromide that was added. Now, this is the common ion effect, but you can also think of this in terms of Le Chatelier's principle. So just like we saw back in question 7, part C, earlier in this video, if we have an equilibrium system and some additional product is added, then Q becomes greater than K, and there should be a net conversion from products to reactants or from right to left. So if additional bromide ions are added in the form of this small amount of solid sodium bromide, then when they are added to the saturated lead bromide solution, this will cause a shift in the equilibrium position for this process. It will cause a shift from products to reactants or from right to left. Therefore, the value for the concentration of the lead ion should decrease after the sample of solid sodium bromide is added. Now, another way that you can process what's going on in part B of question 8 is you can think about it in terms of Q versus K. So sodium bromide is added to the saturated solution of lead bromide. Sodium bromide contains bromide ions. The concentration of the bromide ion increases, which causes a stress on the equilibrium system. And so now think about the comparison of Q versus K. At that moment, since the concentration of bromide ions increased, then Q has become greater than K. And when Q becomes greater than K, there should be a net conversion from products to reactants. So another way of answering part B is the following. Solid sodium bromide is added to the saturated lead bromide solution. This causes the value of the concentration of the bromide ion to increase. Q becomes greater than K for this solubility equilibrium, and there will be a net conversion of products to reactants or a shift in the equilibrium from right to left. The value for the concentration of the lead ion should decrease after the sample of solid sodium bromide is added. Okay, so that is the answer to number 8, part B. Now, let's take a look at question 9 in your packet. In question 9, it says, a student added an excess amount of solid calcium fluoride, which has the formula CaF2, to 2 different beakers, as shown in the diagram above. One beaker contained distilled water, and the other beaker contained 0.50 molar sodium fluoride. So this scenario is very similar to number 7, part C, that I had discussed earlier in the video. The contents of each beaker were stirred thoroughly after the addition of solid calcium fluoride. A small amount of undissolved solid calcium fluoride remained at the bottom of each beaker at the end of the experiment. So this tells us that each of these solutions is a saturated solution because of the presence of the undissolved solid. Assume that the temperature is 25 degrees Celsius. Part A. The value of KSP for calcium fluoride at 25 degrees Celsius is 3.9 times 10 to the negative 11. Calculate the value of the concentration of the calcium ion in each beaker at the end of the experiment. So again, we have calcium fluoride dissolved in distilled water, and we have calcium fluoride dissolved in a solution of 0.50 molar sodium fluoride. This is a great example of the common ion effect. Let's begin with the distilled water solution. So we're going to calculate the concentration of the calcium ion at the end of this experiment. Here is the equation for the dissolution of solid calcium fluoride in water. Calcium fluoride dissociates into the calcium ion and the fluoride ion. There is a 1:2 ratio. So therefore, the concentration of the calcium ion in this saturated solution is X, whereas the concentration of the fluoride ion in this saturated solution is 2X, because 2 moles of fluoride are produced for every 1 mole of calcium. Now we know that the value of KSP is 3.9 times 10 to the negative 11 for calcium fluoride at 25 degrees Celsius. So we can do X times the quantity 2X squared, which equals 4X cubed. Set this expression equal to the KSP of 3.9 times 10 to the negative 11, and then simply solve for X. So 3.9 times 10 to the negative 11 is going to be divided by 4, and then I will take the cube root of that expression. So when I do that math, I get that X is equal to 2.1 times 10 to the negative 4. And so that is not only the value of X, it is the concentration of the calcium ion in this saturated solution of calcium fluoride. So we have now answered the first part of part A. Now let's calculate the value for the concentration of the calcium ion in the other solution that was prepared, the one that was prepared by adding excess solid calcium fluoride to a 0.50 molar solution of sodium fluoride. In other words, there's already fluoride ions present in this solution before the calcium fluoride is added. Now, instead of thinking of this as X and 2X, we already know, based on the given information, that the concentration of the sodium fluoride is 0.50 moles per liter. So the concentration of the fluoride ion is much larger than what it would normally be if we had started with distilled water. So I can go ahead and plug in 0.50 molar for the concentration of fluoride, which is already present in solution. There's not going to be a significant increase in the amount of fluoride that's coming from the calcium fluoride, because 0.5 is a much larger number than what would be present. If you go back and look at the earlier part, 2.1 times 10 to the negative 4 is much smaller than 0.5. So the concentration of fluoride would be 4.2 times 10 to the negative 4, and 0.5 molar is much larger than that. All right, so now I have my KSP expression in which I know the KSP, 3.9 times 10 to the negative 11. I don't know the concentration of the calcium ion, but I know that because of this excess amount of fluoride that was already present in the beaker, the concentration of fluoride is 0.50 molar. Now, I'm going to solve for the concentration of the calcium ion. So the concentration of the calcium ion, if I rearrange this equation, is 3.9 times 10 to the negative 11 divided by 0.5 squared. And so when I do this math on my calculator, I get a value of 1.6 times 10 to the negative 10 moles per liter, and that's the concentration of the calcium ion in this second saturated solution. So now, we have an answer to part A. Compare these two values. What do you notice? Well, hopefully you notice that the concentration of the calcium ion in the second solution is much smaller than the concentration of the calcium ion in the first solution. Again, this is another example of the common ion effect. So calcium fluoride is more soluble in distilled water. Calcium fluoride is less soluble in a solution that already contains fluoride ions. So according to the common ion effect, The solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present in the salt. So the fact that calcium fluoride is less soluble in a solution that already contains fluoride ions, that's a great example of the common ion effect. All right, now let's move on to part B of question 9. It says, explain the difference in the calcium ion concentration in the two beakers in terms of the common ion effect and Le Chatelier's principle. So we have the presence of additional fluoride ions. Calcium fluoride is less soluble in 0.50 molar sodium fluoride than it is in distilled water. So as the concentration of the fluoride ion in the solution increases, Q becomes greater than K. When Q is greater than K, there is a net conversion from products to reactants, shifting the equilibrium for the dissolution of calcium fluoride from right to left toward the solid calcium fluoride on the left side of the equation. And so this makes calcium fluoride less soluble in sodium fluoride than it is in pure water. So that is the answer to part B of question 9. Now let's take a look at question 10 in your packet. So we are given a diagram involving a dropper pipette in which a 1.0 molar solution of potassium iodide is added to a saturated solution of lead iodide. So here's the information in question 10. It says a saturated solution is prepared in a beaker by adding excess solid lead iodide to distilled water at 25 degrees Celsius and stirring until no more solid dissolves. A small amount of undissolved solid lead iodide remained at the bottom of the beaker. Again, that is confirmation that we have prepared a saturated solution. Then, several drops of 1.0 molar potassium iodide are added to the saturated solution in the beaker. So that we can see in that dropper pipette with the few drops of 1.0 molar potassium iodide being added. The contents of the beaker are stirred thoroughly. Assume a constant temperature of 25 degrees Celsius and that the change in volume is negligible. So again, another example of the common ion effect. We have the equation for the dissolution of solid lead iodide with solid PbI2 on the left, and then the aqueous ions Pb, so lead, 2+, and then I- iodide on the right side of the equation. So think about how this equilibrium system for the dissolution of solid lead iodide is affected if additional iodide ions are added to the solution in the form of that small amount of potassium iodide solution that's being added. So in part A of this question, it says, do you predict that the mass of the solid lead iodide present in the beaker should decrease, increase, or remain the same as the result of the addition of that potassium iodide solution? Justify your answer in terms of the common ion effect and Le Chatelier's principle. Hopefully you've seen enough examples of the common ion effect so far in this video that this should make sense that we now have a common ion in that potassium iodide contains iodide, which is going to cause a stress on the lead iodide system. So here is our equation for the dissolution of solid lead iodide, and the stress is going to be an increase in the concentration of iodide. So the addition of potassium iodide to the beaker increases the value of the concentration of the iodide ion, and as the concentration of the iodide ion in the solution increases, Q becomes greater than K. And when Q is greater than K, there is a net conversion from products to reactants, shifting the equilibrium for the dissolution of lead iodide from right to left toward the solid lead iodide. Therefore, the answer to part A, the mass of lead iodide, solid lead iodide present in the beaker should increase. Now, as we take a look at part B of this question, it's a very similar justification, but we're talking now about a different component of this saturated solution. So take a look at part B. Do you predict that the concentration of the lead ion in the solution should decrease, increase, or remain the same as a result of the addition of the potassium iodide solution? Again, justify your answer in terms of the common ion effect and Le Chatelier's principle. So what we have is the same effect in terms of a shift in the equilibrium system, but now we're answering a slightly different question. So this time we're not talking about the amount of solid lead iodide, but rather the concentration of the lead ion. So the addition of potassium iodide to the beaker increases the value of the concentration of the iodide ion, and as the concentration of the iodide ion in the solution increases, Q becomes greater than K. When Q is greater than K, there is a net conversion from products to reactants, shifting the equilibrium for the dissolution of lead iodide from right to left toward the solid lead iodide. But as a result, the concentration of the lead ion in the solution should decrease. All right, well, that's the answer to both parts A and part B for question 10. Now let's take a look at the last question in this packet. This is question 11. In question 11, it says the value of KSP for barium fluoride, BAF2, at 25 degrees Celsius is equal to 1.8 times 10 to the negative 7. In part A, it says a saturated solution of barium fluoride is prepared at 25 degrees Celsius by adding excess solid barium fluoride to distilled water and stirring until no more solid dissolves. Calculate the value of the concentration of the barium 2+ ions in this saturated solution. Let's begin by writing the chemical equation for the dissolution of solid barium fluoride. So we have BAF2 solid on the left, and then we have the barium 2+ ions and the fluoride ions, F- on the right. The KSP expression for barium fluoride is written as concentration of the barium ions times the concentration of the fluoride ion squared. Now, since we don't know the concentration of either one of these ions, then we can let X represent the concentration of the barium ions in this saturated solution. And then since 2 moles of fluoride are produced for every 1 mole of barium, then the concentration of the fluoride ions in this saturated solution would be 2X. Let's plug in those values of X and 2X into the KSP expression. So we have X times the quantity 2X squared, and that equals 4X cubed. We can set that equal to the numerical value of KSP, which is 1.8 times 10 to the negative 7. So all we have to do now is solve for X, and that would represent the concentration of the barium ion in this saturated solution. So 1.8 times 10 to the negative 7 divided by 4, and then we take the cube root of that value, and that gives us an answer of 0.00356 moles per liter. So if we round off that number to 2 significant figures, then the concentration of the barium ion in this saturated solution is 0.0036 moles per liter, or you could write that in scientific notation as 3.6 times 10 to the negative 3 moles per liter. So that is the answer to part A. Let's take a look at part B and see how the common ion effect will be represented. So in part B, it says a small amount of solid sodium fluoride. So again, there's a substance that contains fluoride ions, so that's the common ion, small amount of solid sodium fluoride is dissolved completely into a 1.00 liter sample of a saturated solution of barium fluoride. So you can already anticipate that barium fluoride will be less soluble in a solution that already contains fluoride ions. So we're going to shift the equilibrium from products to reactants, and most likely that is going to decrease the solubility of barium fluoride. So we're going to see a new value for the concentration of the barium ion. So assume constant temperature of 25 degrees Celsius and that the change in volume is negligible when a small amount of this solid sodium fluoride is added. As a result of this experiment, the value of the concentrated the solution, the value of the concentration of the barium ion in the solution has now been reduced to 5.0 times 10 to the negative 7. So if you compare, you can see in the upper right corner of this slide our answer to part A. The concentration of the barium ion was 3.6 times 10 to the negative 3 moles per liter, and now it's been reduced to 5.0 times 10 to the negative 7 moles per liter. So in part B, we have to calculate the number of moles of solid sodium fluoride that was added to the solution. So what we're going to do is put in the value for the concentration of barium, 5.0 times 10 to the negative 7, but we don't know the concentration of the fluoride ion. All we know is that most likely the fluoride ion has been increased, which is causing this decrease in the concentration of barium. Let's go ahead and solve for the concentration of the fluoride ion after this change has occurred. So we have 1.8 times 10 to the negative 7, that's our KSP. Let's divide by the concentration of barium. So divide by 5.0 times 10 to the negative 7. So now we have that the concentration of the fluoride ion squared is equal to 0.36. We'll take the square root of 0.36, and so we get our answer. The concentration of the fluoride ion in this new solution is now 0.60 moles per liter. So how did they get a concentration of the fluoride ion of 0.60 moles per liter? Well, additional fluoride ions were added in the form of sodium fluoride. So the official answer to this question is related to the fact that we had a 1 liter sample, and so therefore to achieve a 0.6 moles per liter concentration of fluoride, this means that 0.60 moles of sodium fluoride solid was added to the solution. So again, it's an example of the common ion effect. An increase in the concentration of the fluoride ion caused a shift in the equilibrium and decreased the concentration of barium. So the correct answer to part B is that a 0.60 mole sample of solid sodium fluoride was added to the solution, and we were able to figure out that number by plugging in the new concentration of barium into the KSP and then solving for the concentration of the fluoride ion after that change was made. All right, well, that is the answer to part B of number 11. This is also the last question in the packet, so we have now reached the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.